Hi, welcome to Ushendra's engineering tutorials. Yet another important video from the playlist Measurements and Instrumentation, something about a Q meter. What is a Q meter? What is the intention behind the circuit Q meter? What it does actually. Right? Before going to that one, we need to have some fundamentals. Let me remind you some fundamentals which you have forgot. You might have been taught in your previous grades, but you might have forgot by now. So let me give a small recollection of that one. And what's a Q meter? What's the need of a Q meter? And what is resonance? We often come across what is resonance. The term resonance is very much interlinked with the Q meter. Q meter is a circuit which is intended to measure the quality factor of inductors and capacitors, and resonance that works under the principle of resonance, very much interlinked. So what is resonance? In your previous grades you might have come across this one, the inductor. We may have an inductor L and a capacitor like this one, and the reactance of the inductor, it's XL, given as XL, and the reactance of the capacitor, it's XC, right? And going ahead, it is written as omega L, and this which is equal to 1 upon omega C, C being the capacitance, L being the inductance, right? And more precisely, this omega, it's in radians, in hertz it's 2 pi f, it's 2 pi f L, and which is equal to XL. On the other hand, this which is equal to 1 upon 2 pi again f into C. See, the very basic fundamental knowledge. These two are here. The reactance of inductor and the frequency are directly proportional to each other. When the frequency increases, when this factor, here in this expression, frequency and these are directly proportional to each other. When there is an increase in the frequency, even this increases, and when there is a decrease in the frequency, even this factor decreases. Whereas coming to the capacitor, the capacitive reactance and the same frequency, what I've told you right now, this frequency are inversely proportional to each other. This one, we have this one, like the inductive, the capacitive reactance and frequency in this expression are inversely proportional to each other, this being in the denominator. With the increase in the frequency, this comes down. With the decrease in the frequency, this goes up. If these two components are made a part of a circuit, and if we vary the frequency, right, if these two, inductor and capacitor, made a part of a circuit and varying the frequency, with the increase in frequency, one reactance, like inductive reactance, goes on increases, and capacitive reactance, if this inductor and capacitor made a part of a single circuit, this will be XL, and XC would come down like this one, and at a particular frequency these two will be equal. This is coming down, this is going up, and this is coming down. At a particular frequency going on increasing, at a particular frequency these two will be equal. XC, the reactance XL, will be equal to XC. In other words, omega L will be equal to 1 upon omega C. So that particular frequency at which the inductive reactance being equal to capacitive reactance, that condition is known as resonance, and that frequency is known as resonance frequency. This forms the very basis for working of a Q meter. Considering a circuit, supply, a source, AC source, and a series RLC circuit, right? R like this, and inductor L and a capacitor C like this. Let the supply voltage be E, this one, let the supply voltage be E, and voltage across capacitor E, C. What we have is, yeah, it's a source, AC source, so definitely, yeah, this one, AC source with some variable frequency. We are not touching that one. It's a variable capacitance over here. It's a variable capacitance. Now we are changing the value of the capacitor. Even that can be done. Not only frequency. When under this condition, even capacitor can be varied, and this can be varied. So at some particular capacitance, this will be equal to this, definitely. And under this condition, the capacitance C is varied. Here it's a capacitance C, and for supposing, yeah, there is some balance at a particular frequency, there is a the capacitive reactance will be equal to inductive reactance, and under that condition some current I naught will be flowing, I naught, right? So what will be I naught, and it will be more easier to understand if we go for the phasor diagram, right? So having a basic knowledge on phasor diagram, see, I naught will be flowing in the circuit under resonance. There are some other methods to know that where the resonance has occurred, that will be dealt while dealing with the series and shunt connection of the Q meter. For the time being, this is the basic, right? By varying, let's suppose by varying the value of the capacitor, we have achieved the resonance, and under resonance I naught will be flowing. The circuit, this source giving rise to I naught, the I naught will be flowing through the resistor, the same I naught, all these components being in series, I naught will be flowing through this and this and this, right? So having a knowledge on phasor diagram will be more convenient to understand this one, what happens actually in the circuit, right? So taking I naught as reference, I naught is flowing through R and giving rise to a drop across the voltage, a drop across the resistance R, a voltage drop across resistance R. And from the basic knowledge of a vectors phasor diagram, the resistive voltage is in phase with the current flowing through the resistor, right? And so these should be in phase with each other, like this here. This would be I naught into R, the drop across the resistance. On the other hand, the same I naught is flowing through the inductor, and the voltage drop across inductor will be leading the current. We already have this current. The voltage drop across the inductor will be leading this one. So how can that be written? It's it may be drawn from here or here. So it may be like we are bothered about this one, right? So how to write the drop across inductor? It's omega L. On the other hand, the same I naught is flowing through the capacitor, like this. The same I naught is flowing through the capacitor, and from the basic knowledge of a phasor diagram, the drop across the capacitor will be lagging behind the current passing through the capacitor. The voltage across the capacitor will be lagging behind 90 degrees behind the current through the capacitor. So we already have that current which is flowing through this capacitor, and the voltage drop across the capacitor will be lagging behind 90 degrees behind the capacitor, like this one. And how to write that one? Omega 1 upon omega C is this one. Okay, so this one we can clearly see that this is in one direction and this is in another, opposite. These both are in opposite direction, and when at resonance this will happen, in the sense this will be equal to, this magnitude will be equal to this magnitude. Being in opposite phase, these two gets cancelled. We don't have these vectors anymore, and we are left with only this one. In the sense, the circuit will be purely resistive under resonance. The circuit will be purely resistive because this reactance due to the inductor reactance due to capacitor gets cancelled out, being this much, like positive 90 and negative 90, that gets cancelled out, and the circuit will be completely resistive under resonance. This is an important point to be remembered. All the discussion starts from as if we have obtained the resonance condition, right? Like what I mean is, at resonance, what will be the voltage drops? At resonance, we have tuned the capacitor to resonance, we have obtained the resonance, and I naught will be flowing in that case. So how can that, this voltage drop is equal to this drop plus this drop plus this drop. How can that be written? It's a E, supply voltage E is equal to I naught into this one, R plus XL plus XC. From the knowledge of the phasor diagram, these two are out of phase with each other, being equal in magnitude. these two, the inductive reactance and capacitive reactance, are 180 degree out of phase with each other, being equal in magnitude. It may be plus 5 minus 5 in terms of magnitude, like that, plus and minus equal in magnitude. These two gets cancelled out at resonance. Remember the underline at resonance. Everything is happening at resonance, and at resonance, when these are cancelled out, the circuit will be purely resistive, and E will be equal to I naught into R. At resonance, this is an important equation to be remembered. We'll have to get back to this, right? On the other hand, what will be EC? The drop across EC at resonance, I naught is flowing through the capacitor. So what will be EC? EC will be, sorry, I'll write over here, EC will be equal to I naught into the capacitive reactance XC, still, which is equal to, and that too, this equation is for the under the condition resonance. So I naught can be substituted with XC equal to XL under resonance. So that will be equal to I naught, the magnitude, writing the magnitude, I naught XL is omega L. This is for the voltage drop across capacitor under resonance, right? This is the supply voltage, and this voltage being this one at resonance, EC will be this one. Now this is another important expression to be remembered. And what is the definition? What according to the definition is a quality factor Q? Q is defined as the inductive reactance upon the resistance. Inductive is the ratio between this one, XL by R, which is equal to R as it is. Once again at resonance, XL will be equal to XC. These two, like if you have this one, we can substitute with this one, or if you have, we can go back to this. In other words, it's XL omega L upon R, which is equal to XC 1 upon XC, reactance, capacitive reactance, omega C into R. Q equal to this one, has these many forms under resonance. Remember, it's under resonance. I repeat, the quality factor is defined as XL upon R. So where did we get this equation from? R as it is. At resonance, XL will be equal to XC, and this is what, and XL being omega L upon R. This is the important relationship. Focus on this one. You missed this one. Focus on this one. It's under, once again, under resonance. Where did I get all this from? Under, when the circuit is subjected to resonance by varying the capacitance C. On the other hand, guys, getting back to this ratio, what will be this ratio? EC upon E. What it may be? EC upon E. EC is from this one, I naught at resonance, once again, I naught into omega L upon I naught into R, the supply voltage, and something else cancelled out here. I naught and I naught gets cancelled. We are left with omega L upon R. The discussion is completely under resonance. So what this is, guys, match this one to something else. Omega L upon R, it's Q. And so EC upon E is equal to the quality factor, in the sense which implies the drop across the capacitor, EC is equal to Q times the applied voltage. You might find this statement, the drop across capacitor under resonance for a series RLC circuit, under resonance, the drop across capacitor is equal to Q times the applied voltage. You will find this statement in whatever material you study, or else comment me in this, or else drop a comment in the comment section. No, we didn't find that. You will find whenever, if you're studying, if you're going through the Q meter, and definitely you will come across this statement. What is that? The drop across capacitor is equal to Q times the applied voltage. Now this is an important equation which forms the basis of a Q meter. right? Please make a note. Everything one after the other. From the phasor diagram we get this one, and from the definition we get this one, and finally we reach this. At resonance, the voltage drop across capacitor is equal to Q times the applied voltage E. E is the supply voltage. You can find the statement, the drop across capacitor at resonance, the drop across capacitor is equal to Q times the applied voltage. Please make a note, please. Two methods of evaluating the quality factor of unknown impedances. Low impedance, series method is selected, and the unknown impedance, if the unknown impedance is very high, we go for the shunt connection. Now this is for a series connection. I have intentionally left this one. The unknown impedance whose quality factor is to be measured is connected over here. It's a unknown Z. You can find in your, match your circuit diagram with mine. It's a Z, unknown impedance, whose quality factor is to be determined. And also, other than this, we have a switch connection over here. We have a switch connection in shunt with this one. We have a switch connection over here. Two readings to be taken. Let me explain what is happening. It's a capacitor, and these two are in series. The working coil, this is known as a working coil, and the impedance whose quality factor is to be measured are in series, and so this connection is known as a series connection, right? And what according to definition, the quality factor Q is defined as X at resonance XL upon R, that R, which is equal to R as it is. XL will be equal to XC. Even these two are true, and if this is true, even this is true. Remember, we have to plug in some value as we go on with the derivation. If this is true, even this is true. Another important equation from this one, R will be equal to XL by Q. Even this is true, which is equal to XC by Q. Even this is true from this expression. It may be, in general, R1 may be equal to X1 by Q1, and R2 equal to X2 by Q2. Even these are true, valid equations. We will come across all this one. If this ratio is found out, we have to substitute this one, or vice versa. This one can be plugged in with this one, and everything like this one. For supposing the C is tuned, not touching, and another condition is that the switch is closed. With this connection, we don't have this impedance, unknown impedance doesn't exist in the circuit, and C is tuned to C1. We don't touch the value of Rn. This one, C is tuned to obtain the resonance condition. The maximum value indicates that the circuit is under resonance, and under resonance, when C equal to C1, what will be the equation we can write down? It's at resonance, the inductive reactance is equal to the capacitive reactance XC. More precisely is XC1. Why? Because we change the value of capacitor from C to C1, so this condition comes into the picture, and XL being omega L will be equal to XC 1 upon omega C1, right? And this is an important relationship once again. For the second reading, subjecting C equal to tuning for second reading, in the sense it's open, the switch is open, Z comes into the existence in the circuit, and let the impedance be XS in series, right? Because the impedance is in series with this one. And what is this impedance? It's XL, and this be, now the capacitor is tuned to C2. It's no more C1, it's another value of capacitor. We are not touching anything over here. We are changing the value of capacitor to obtain the resonance. That can be done. And XC, the reactance due to capacitor, XC2, right? From here, which you miss, the derivation part, which you miss, what happens is these two are in series, and this can be neglected. Actually, the reactive, it doesn't impose any resistance in the circuit, the internal resistance being very small, in the order of 0.02 ohms. I remember, this doesn't impose any reactance or resistance. As far as reactances are concerned, we can neglect this one, right? This this impedance, the series combination of this impedance is in parallel with this one. How to write that one? XL plus XS, the unknown impedance, the inductor reactance plus the unknown impedance reactance is equal to XC2, right? Because the capacitor is tuned to another value, that is C2. The previous one, when the switch is closed, that is C1, and switch is open, we are including the unknown impedance, and that the capacitor takes another value to obtain the resonance, that is C2. And from this it's true, like XS, the unknown impedance, will be equal to XC2 minus XL, right? So hope you understand this one, which is equal to, what is XC2? It's a capacitive reactance. It will be 1 upon omega C2 minus XL omega L, which is equal to, this takes up the form XS is equal to 1 upon omega C2 as it is, minus, guys, over here omega L will be equal to 1 upon omega C1. That, substituting that one, we have 1 upon omega C1, right? You are confused, you don't get this derivation. Like if you are a beginner, this is the problem you have. This is the, make a note, right? These two are in series. This series combination is in shunt with this one, and this comes into the picture. So can you see this equation? And simplifying this one, it will be LCM, it's a omega C1 C2, and cross multiplying will be having, already we have omega, so it will be C1 minus C2. Hope you can see this one. XS, you will see this expression, XS is equal to this C1 minus C2 upon omega into C1 C2. And you have another statement from here, continuation to this one, you will have another expression. If C1 is larger than this one, this entire equation will be positive. That indicates the unknown impedance is inductance, no lagging, right? And on the other hand, if C2 is larger than this one, the negative appears over here, the resultant, the negative will be appearing over here, and that indicates the unknown impedance is a capacitive. Make a note, you have that statement. After this expression, from the, it will be saying like that, from the above expression, if C1 is larger than this one, that becomes positive, and XS will be inductive impedance. And if this the reverse case, C2 being larger than C1, this will be negative, and so the XS will be capacitive impedance, right? This one. If this is true, guys, if this is true, even another equation is true. Here, what it is, here you have to focus on this one. RS is equal to like this one, X2 by Q2, from this one itself, from this very equation, minus X1 by Q1. Even this is true from this expression, very expression, right? It may be having a quality factor, even this will be having a quality factor, and quality factor, we don't know the quality factor of this one, so that can be written in terms of this one, right? Even this is true from this very equation, we can write this one. From this, what as we go on, what it is what is X2? We change the capacitor, so that would come into the picture. It can be written as XC2 by Q2 minus XC1 is equal to same XC1, it may be XC1 XL, XC1 by Q1. We can plug in with XL also, because this is true, no change. This cannot be XL because we changed this one, so that will be this. And an important equation, please make a note. I know you missed it, you missed this one, you are confused with this one. Well, let's make more transparent. I understand you're confused with this one, it's a tedious one to understand. What I mean for a beginner, if you're an expert, that doesn't mean if you're a beginner you are confused. What I mean is, did you understand this point? XL, the series combination, XS is equal to this one, this is in shunt with this one, so XC2 Is that okay? This is for the reactances, XL, XC, XS, XS, the impedance of the unknown which is in series, so it's XS, right? If this is true, even the quality factor of these two will be equal to this, right? Even the quality factor of these two is equal to this. I can write that same, like from this one, XS is equal to XC2 minus XL, we got this one, right here. Is that clear for you? Now coming back to the quality factors, even the quality factor of this plus this is equal to this. The quality factor of this plus the quality factor of this is equal to the quality factor of this. Is that clear? So I don't know the quality factor of the unknown impedance. It's unknown, it's completely unknown. I don't know the quality factor. The main objective is to evaluate the quality factor of this one. So how do I write down that directly? No, right? So once again I repeat, the quality factor of this, similar to this one, the quality factor of this plus the quality factor of this is equal to the quality factor of this. Did you get this one? Rewind and see if you don't, right? So I cannot write directly the quality factor of this one, I don't know. I can write in terms of its resistance. It may be like we have the definition for quality factor, Q equal to X by R. It may be XL by R or something else. So from this one, what can I write? R equal to X upon Q. That's what I have written. I have written this one. I don't know this. So it will be, if it's XS, it will be RS, right? And this for this one. And for this one, what it is? It's this one. It's RS. I cannot write down this one. So RS will be equal to this quality factor of this one. How to write down in terms of this? In terms of this one, it's a XC2 upon Q2, the quality factor Q2, minus this one, similar to this one, minus this one. What will be that? XL by Q1, or else XL by 1, or else it's XL by 1. Raising here itself, it's XC1. Why? Because in the beginning, for the first condition, when this was closed, in the absence of this, XC1 is equal to XL. Recollect that one, write the notes, right? Here, this is the one. This is where I got this one, right? Is that clear? Now XC2, it's XC2. What is XC2? It's a capacitive reactance that can be Q2 as it is, XC2 1 upon omega C2 minus XC1 1 upon Q1 as it is. XC1 is omega C1, which is equal to RS. Guys, at least now am I able to reach you? Please rewind and see this one, right? Nothing, I didn't hide anything. It's very transparent. Please make a note. This is the one. Now we have the term XS and we have the term RS, that which gives us Q of S. Yeah, going back, Q equal to X by R, Q equal to X by R, and so Q1 equal to X1 by R1, Q2 equal to X2 R2. So in the sense, QS, the quality factor of the unknown impedance which is in series, right? The quality factor will be equal to, what is that? XS upon RS. Hope you can find this expression. You can see this, right? Simplifying for RS, what we have is RS is equal to Q2 as it is in the denominator, Q2, XC2 is the capacitive reactance, so what we have is 1 upon omega C2, right? Minus Q1 as it is in the denominator for the second term, and XC1 is equal to XL. I've told you like how I got XC1, 1 upon omega C1, and simplifying this one, what we have is common omega C1, C2, Q1 and Q2 in the denominator, and cross multiplying, what we have is omega already we have, so omega we don't have, C1 Q1 minus C2 Q2. This is for R of S, you can find this one, you may be finding this one. R of S is this. Okay, so what according to definition, quality factor Q is equal to what? X by R. It may be Q of S, the quality factor of this one may be X of S by R of S. What are you waiting for? Plug in the values of this and obtain the quality factor of the unknown impedance. Q of S is given as here. Q of S will be equal to that one. Q of S, X of S, that one, how it is? C1 minus C2 upon omega into C1 C2 into, this is R of S in the denominator for this expression, so just flipping up, we have omega C1 C2 Q1 Q2 upon, this comes in the denominator, it's a C1 Q1 minus C2 Q2. Guys, something gets cancelled over here almost at the end. Omega C1 C2, omega C1 C2 gets cancelled. Can you see this? This gets cancelled. Omega C1 C2, omega C1 C2 gets cancelled. And the quality factor, finally, the quality factor of the unknown series, quality factor of unknown impedance connected in series is given as that one. Q1 into Q2 into C1 minus C2, and in the denominator what we have? C1 Q1 minus C2 Q2. This is my final expression for the quality factor of unknown impedance which is connected in series and in the series connection. Hope you find this useful. If you find this useful and helpful, please share my videos. Subscribe to Ushendra's engineering tutorials. This is for today's video. Thank you so much. Thank you so much for being with me. Stay home, stay safe.